In this section, we want to take a look at a pair of graphs that will allow us to visualize quantitative data. The first graph that we'll look at is referred to as a stem plot, which is a shorthand way of saying stem and leaf plot. In a stem plot, what we do is take each number and break it up into a stem and a leaf. In this case, our stem plot provides a key which shows that the number 28 would be broken up into a stem of 2 and a leaf of 8. And we can use that key, that idea, to translate the rest of the information from our stem plot to the original numbers that were provided, which is what we're asked to do in example 1. The stem plot below depicts the miles per gallon for 13 cars. We want to list the individual gas mileages for each car included. So in our row that starts with a stem of 1, we have an 8 on the other side. That would translate into a data value of 18 miles per gallon. In our row that starts with a stem of 2, our first data value would be 21. Then we have 24, 27, 28. And if we notice here, the 8s are repeated, the 9s are repeated. Each time that digit is repeated means that that number came up an additional time as part of our data. So there were 2 different cars that were measured as having 28 miles per gallon gas mileage, and 2 cars that had 29 miles per gallon. Then moving on to the third row, our first data value here would be 31. 31 miles per gallon occurred for another car, and 38. And then in the last row we have 42 and 44. So we can see how we can translate back and forth between that stem plot and the list of actual data values. This is, again, just one method for visualizing that information. It lets us see things like how many data values fell in a particular category or in a particular range. So everything from 20 to 29 falls in this second row, which has the highest level of representation since it has the longest list of leaves following it on the right. In example 2, we have another stem plot, which depicts voter turnout in a small town for 13 elections. We want to list the voter turnout for each year included. If we notice, the stem is a little bit different here. It consists of 2 digits, and our key again is telling us what's happening with the stem and the leaf. So a number like 566 is being broken up into a stem of 56, and my circling is a little sloppy there. That last 6 on the end is our leaf. So in this case, our first row would give us the number 456. The second row would give us 461. And now in the third row, we start getting more than one value falling within that range. So we would have 474 and 479. In the next row, 484, then 493, 508, 515. When we get to the row that starts with a stem of 52, we can notice that there aren't any numbers on the other side, on the leaf. It's important that that's left blank. The alternative would be maybe putting a 0 there to indicate that no values occurred, but that would suggest that the value of 520 existed in our data set. Since it's blank, it means there are no values between 520 and 529, so we don't want to include that 0 though, we just leave that blank to indicate no values fell in that range. So we would skip to the next row, which would give us 535. We have another empty row, so we skip to 554, 566, 579, skip again, and we get 595. Stemplots are best for integer values. They're not going to work well if we're dealing with fractions or decimal answers. We need moderately sized data sets. These would start to get a little unwieldy if we had too many data values, and especially if the range of values was really large. So if this went from values of 0 up to, say, 3,000, this stemplot would become pretty unwieldy. And one perk of stemplots is that they show all of the individual data values. So none of the individual data values are lost when we convert it into this visual representation.